Have you ever wondered why dogs bark at something far away that you can't even hear? That's because your ears have some pretty clear limits. Welcome to the fascinating world of sound and hearing. Let's dive into what our ears can and can't catch. The average human ear is like a tuned musical instrument, perfectly sensitive but within a certain range. We can usually detect sound frequencies from 20 Hz to 20,000 Hz. That's called the audible range. Sounds with frequencies below 20 Hz fall into something known as infrasound. They're too low pitched for our ears but can be produced by natural events like earthquakes. On the other end, sounds above 20,000 Hz are called ultrasound. These are too high for humans to hear but incredibly useful in technologies like sonar and medical imaging. Now here's the bittersweet truth. As we age, our ears tend to lose their superpowers. Most adults can't hear tones above 15,000 to 17,000 Hz, and shouting at your grandparents in 19 kHz won't help. It's a normal effect called presbycusis, and long-term exposure to loud sounds can accelerate this. Also, our perception of pitch isn't linear, it's logarithmic. That means if you double a sound frequency, the tone doesn't just get higher, it feels like it jumps noticeably. One key relationship here is between frequency and time period. It goes like this: frequency equals 1 divided by time period. In other words, if a wave has a short time period, the frequency will be high and vice versa. That's why rapid vibrations give us high-pitched sounds. Now, frequency isn't the only factor that decides what we hear. Intensity and loudness matter too. Even if a sound falls within the 20 to 20,000 Hz range, if it's too soft or faint, it might still go unnoticed. So, your dog might hear something real, it's just whispering in a frequency or intensity we can't catch. Okay, here's a fun thought. If humans had the hearing of a bat, we'd literally hear our phone screen ping from across the neighborhood. Truth is, while our ears are pretty impressive, some animals blow us out of the water, sometimes quite literally. Different animals have different hearing ranges thanks to natural evolution. For example, dogs can pick up sounds all the way up to around 45,000 Hz, which is more than double the human limit. That's why dog whistles are silent to us but crystal clear to our canine friends. Bats are the real superheroes here. They can detect frequencies between 20,000 and 120,000 Hz. Why? Because they use echolocation, sending out ultrasound waves and interpreting the echoes to fly at night without crashing into things. On the opposite end, elephants are the low-frequency champions. They can detect infrasound, frequencies below 20 Hz, and use it for communicating long distances, even several kilometers apart. That deep rumble? It might be an elephant saying hello from 5 hills away. The range of hearing in a species, from minimum frequency to maximum frequency, is written as delta F equals F max minus F min, where F max is the upper audible frequency and F min is the lower. So, species evolved to use their auditory superpowers based on their environment and survival needs. And believe it or not, we use this knowledge too. It helps us design better alert systems, special dog whistles, motion detectors using sound. Our understanding of animal hearing isn't just fun trivia, it's practical tech. Imagine listening to a sound so high-pitched that nobody on earth could hear it, including you. Sounds like it belongs in a spy movie, right? Welcome to the world of ultrasound, frequencies beyond 20,000 Hz. Now, even though humans can't hear ultrasound, it doesn't mean these waves are useless. In fact, they're incredibly valuable. Ultrasound waves tend to travel in a narrow beam. They're highly directional, which makes them great for bouncing off surfaces and returning with useful info. These waves travel as longitudinal waves, just like most sound, and they reflect really well when they hit a boundary between two materials. This property is exactly what powers tools like sonar and medical ultrasound machines. In sonar, which stands for sound navigation and ranging, a blast of ultrasound is sent out, and when it hits an object, it reflects back. We then measure the time delay between the emission and the return. Using the speed frequency wavelength formula, which goes like this: speed equals frequency multiplied by wavelength, we can analyze how far the object is. But to directly calculate the distance based on echo time, we use another formula: distance equals speed multiplied by time divided by 2. That division by 2? It's because the sound wave makes a round trip there and back. Beyond C and body scans, ultrasound has some fun lab uses too. Ever heard of ultrasonic cleaning? It uses a process called cavitation. Basically, sound waves create tiny vibrating bubbles in a liquid, which scrub dirt off surfaces, even in cracks and corners you can't reach with a brush. In physics, even what we can't hear can make a really loud impact. Let's switch to the other end of the frequency scale, the super deep, rumbly world of infrasound. These are sounds with frequencies less than 20 Hz. And although your ears can't pick them up, your body might still feel them. Ever stood near a volcano or in a thunderstorm and felt that low rumble deep in your chest? That's infrasound at work. It's not just a soundtrack to dramatic movies. Volcanoes, earthquakes, and even some massive storms naturally produce infrasound. And certain animals, like elephants and whales, take full advantage of it. They use infrasound to communicate across vast distances. Since these waves have very long wavelengths, they don't fade or weaken easily. That means they can pass through miles of Earth's crust or thick atmosphere with very little energy loss. The basic wave equation still applies, even here: speed equals frequency multiplied by wavelength. In infrasound, the frequency is less than 20 Hz, but because the wavelength is so long, speed stays useful and measurable. Here's what's fascinating: infrasound is now used for saving lives too. In seismic zones, sensitive infrasound detectors can sense upcoming earthquakes before conventional instruments pick them up. It's like hearing nature whisper a warning before it screams. Whether it's tiny or thunderous, sound can teach us a lot about the forces around us. Now for a quick check to see if our ears are doing their job, let's test a tuning fork. Say we've got a fork vibrating at 17,000 Hz. The question is this within the hearing range of humans? Alright, let's recall the hearing range condition. A sound is audible to humans if its frequency f fits between 20 Hz and 20,000 Hz. Mathematically, f must be greater than or equal to 20 Hz and less than or equal to 20,000 Hz. So let's substitute. Our tuning fork's frequency is 17,000 Hz. Clearly, that fits in the range of 20 to 20,000. Therefore, the sound should be audible to the human ear. But hold on, there's a twist in the tale. While this sound is definitely within the theoretical hearing range, in real life, some older people may not actually hear it. That's because the ability to hear high frequencies drops with age, a condition called presbycusis. So depending on the crowd, they may or may not hear that high-pitched tone. Conclusion: this frequency is within acceptable limits for auditory experiments in physics labs, especially for younger students or individuals with healthy hearing. So ring that tuning fork, but maybe don't bet your grandpa can hear it. Let's bring it all together. The human audible range spans from 20 Hz to 20,000 Hz. Sounds outside this range are inaudible but still scientifically and technologically important. You'll recall the key wave formula: speed equals frequency times wavelength. And when using echoes in sonar, we compute distance using the equation distance equals speed times time divided by 2, since the wave goes to the target and back. There's also the relationship between frequency and time period. Frequency equals 1 divided by time period. Infrasound, meaning frequencies below 20 Hz, shows up in earthquakes and animal calls and is even used for early disaster detection. Ultrasound, above 20,000 Hz, powers medical imaging, sonar systems, and industrial cleaning, all due to its short wavelengths and strong reflections. And remember, other animals hear much differently than us. Bats, dogs, elephants, each evolved with hearing tuned to their survival needs. So, the limits of hearing are not limits of usefulness. Sound waves, whether we hear them or not, are all around, packing surprising power. That's it for today's concept. Physics truly sounds amazing when you follow the waves. See you next time for more fun with forces and frequencies.